Hello, hello. Welcome, everybody. Hopefully you can hear me and see me okay. But welcome to our A-level chemistry web class on enthalpy. This is our one of our revision sessions. So this is going to be aimed at year 12s. So we're looking at enthalpy, one of the aspects of chemistry which comes up in A2 as well. So it's really useful to know enthalpy as a year 12 as an AS student, so you can build on it for year 13s. Yeah, so this is our Sunday session on enthalpy. Please feel free to say hi in the comments if you're here. It's lovely to see you, and if you are a newbie, then welcome to our Sunday sessions. If you're an old hat, if you've been coming to these sessions all year, then welcome back. We're going to give it a minute or so just so that people can arrive and we can settle in. But again, please feel free to say hi in the chat. I will do my best throughout the session to answer all and any questions that you have. And so, yeah, if you wanted to do that, you can pop that in the chat. I should be able to kind of read them as they come up. If I do by any chance miss your question though, please feel free to pop it in again, because sometimes they scroll past and then we don't see them. So yes, we'll get started in a second, but yeah, this is our A-level chemistry web class, our Sunday session revision class on enthalpy. We'll get started in just a sec, but welcome if you're new, welcome back if you have been to these sessions before. If you haven't already, please feel free to download the slides for this session, so it should be in the description below, and that'll give you the opportunity to write your own notes, to go ahead if you want to and have a think about what's the information we're looking for, what can you recall, and then also you can save these and use them again for revision later down the line. So always useful, and these web classes should be saved on our what's it called, on our YouTube channel, so you can come back and watch these at a later date as well, if you so choose to. Also, please feel free to go and have a peruse through the other classes that we've got. We've got many web classes saved, so feel free to go and have a look at those. You can download those slides as well and have a go at those, etc. So it's all good revision. Hello, Simba, nice to have you here. Welcome. Right, so I reckon we will get started in a second. But yes, of course, if anybody has any questions or anything and you want to ask them, just pop it in the chat and hopefully I will be able to have a look at what you're asking. Okay, so a little bit about me. I am Alyssa. I've been teaching A-level chemistry for nearly 8 years now, actually. And I also teach GCSE science. I teach science from Key Stage 3 all the way up to A-level, but chemistry is my fave. So I definitely like teaching chemistry. I am the lead chemistry teacher here at SnapRevise, and I have a PGC in chemistry or science, but specialising in chemistry from Oxford University. Oh, good question. How can I download? Are you asking about the slides? They should be a link in the description. You should just be able to, oh, there you go. It has just been posted for you, so you should be able to find the booklet at that link, and then you can make your own notes as we go along. So our objective for this session, we should hopefully be done in just under an hour. We're going to be understanding the concept of enthalpy change. So what is it? We're going to look at Hess's law and how to apply it. And I am huge on the don't just rote learn it. I think A-level chemistry, you can't just rote learn things. Some things you do have to rote learn, but the vast majority, I'd say 80% of A-level chemistry syllabus, you can rote learn it, but it's just not going to be as useful. So we'll hopefully try and understand Hess's law, and then we're going to have a go at making some simple calculations with enthalpy cycles as well, again, by applying our understanding rather than just rote learning. We're not going to look at enthalpy of neutralization. I think that only comes up in one specification, and I can't remember which one it is. Might be at XL. We'll check in a second. And we're not going to look at any trickier enthalpy cycle questions. They do come up again in A2, and there's an added layer of complexity because there's different processes and concepts that are brought in as well. We're just going to stick with the more basic year 12 AS content stuff using combustion and formation. Okay. Hello, Al, as well. Hi, nice to have you here. So if you're AQA student, these are the spec points that we're going to be covering. So make sure you're confident with what they're asking, how much detail they want, etc. It's all laid out for you in your specification, and specifications are so useful. They're literally a checklist for students as to what is expected from them. So it's a really good idea to get comfortable with your specification. OCR, oh, it's OCR, sorry, not Edexcel that do neutralization. So OCR, this is the spec points that we're going to be covering from you, but bear in mind we're not covering enthalpy of neutralization in this web class. The theory and concepts are all very similar. You just need to apply it to neutralization. So hopefully you can do that yourselves. And Edexcel as well. These are the spec points we're going to cover from you. But again, even though it's not been circled this time, we're not looking at neutralization. So it is in Edexcel. Okay. So what do we already know? So a lot of this is actually GCSE level, but it's a good thing to revise it. And we do need to revise these things at A level. So can anybody tell me what is an endothermic reaction? So I'm not, or endothermic process, but I'm talking here specifically about a reaction, or we're going to be talking about reactions. What are endothermic reactions? How do you recognize an endothermic reaction as opposed to an exothermic reaction, let's say? Anybody know? So a reaction that uses thermal energy, you're not wrong, but for A-level chemistry, we have a very specific definition that talks about the movement of energy. So you're hinting at it by saying using thermal energy, but unfortunately, if you gave that definition in an exam, you wouldn't be given the mark, because you do need to be a little bit more specific about the flow of energy. Okay, lovely. So it's taken in from the surroundings. Nice, we're getting a little bit more detail here, that's good. So energy is taken in from the surroundings into the system. Yeah, good, lovely. Tresford, we're absorbing energy into the system. Oh, well, very good then, Jackie, very nice. Yeah, good. Enthalpy is one of the key bits of chemistry, so it's a good one to be in. Good, so an endothermic reaction, or anything that is endothermic, is a process or reaction, if we're talking about reaction, a process that has a net thermal energy transfer or heat energy transfer. Energy transfer from the surroundings to the system. How do we remember that it's endothermic? Hello, I'm not gonna pronounce your name properly, so apologies. Quadjo, welcome, nice to have you here. We're just going through some basics, some what we already know. Does anybody have any way of remembering the difference between exothermic and endothermic? So exothermic is the opposite of endothermic. So it's a process or reaction. We're doing a reaction that has a net heat or thermal energy transfer from the system to the surroundings, in this case, let's try and spell that properly, the system to the surroundings. How do we remember which is which? Does anybody have a way of remembering which is which? So in chemistry, we're very interested in what's happening to something, to a thing. And that thing, or the object that we're studying, the matter that we're studying, is the system. That's the thing we're interested in for the most part. So when we're talking about endothermic and exothermic processes, we want to know what's happening to the system. So is the system gaining energy, or is the system losing energy? So with an endothermic process, energy is entering the system. Endothermic, entering, yeah, exactly. Exactly. So then exothermic, as in energy is exiting the system. You can see the prefaces, the beginnings of the words are the same. So it's a nice way to remember it. So energy is entering the system, it's going into the system from the surroundings, or exothermic energy is exiting the system, going into the surroundings from the system. Prefixes, exactly. Yeah, lovely. Okay, so I've just mentioned what the system is. The system is the matter, the stuff, the object that we are studying, or the objects that we are studying. The matter we are studying. So it's a thing that is important to us, or the thing that we're interested in at the moment. And then the surroundings is just everything else. Any other matter. Okay, so if anybody has any questions, put them in the chat. I will try to have a look at them, and if I ignore them for any period of time, just put them in again, because it might be that I just haven't seen them. Okay, so let's have a go then. So part one, we're going to chat about enthalpy. What is enthalpy? What is enthalpy? Why is it important to us? What is it? What are we measuring? What is enthalpy? And therefore, what is an enthalpy change? Does anybody know? What is enthalpy? And usually we're very specific with our word use. In all of science, we're very specific with our word use, but chemistry, is the same. We're very specific with our word use because lots of words in chemistry have very specific meanings. Enthalpy. Yeah, lovely, Raihan, exactly right. It's the measure of the total energy of a system. And enthalpy is per mole. Okay, so enthalpy is a measure of the total energy of a system. And our units, we'll come to actual units in a second, but it's energy per mole of substance, per mole of stuff. So an enthalpy change is the transfer between the system and surroundings. So the transfer of energy, and the way that we look at energy transfer, this is going back to key stage 3 energy transfers, is heat energy, heat being the transfer of energy. So it's the transfer of energy, specifically heat energy, because that's how it is being transferred between the system and the surroundings. And because, again, we're very specific about what the system is, enthalpy change should have a positive or negative value. It should have a sign, because the enthalpy change, the change is either going away from the system, out of the system, or into the system. Okay, so it's a vector quantity. It must have a direction to do with whether it's going in or out the system. Okay, what about the symbol between, what's the symbol of enthalpy? Anybody know? Oh, Tresswood, if you want to drop an email to hello@snapprovise.co.uk, they can get you connected, or if you go to the SnapProvise website, there's more information on there about how you can join our web classes and things like that. So please feel free to go and have a look at that. So the snapprovise.co.uk, or here's the email address for you as well. Yes, good, thank you, Raihan, exactly. Apologies if I said your name wrong, but delta H, delta being the triangle, means change in. So delta H is our change in enthalpy. But absolutely right. H, just a capital H, is our symbol for enthalpy. So whenever you see H, it means enthalpy, but it's usually accompanied with the delta symbol, the change in symbol. Yeah, lovely, really nice. Units, what are our units? And what do we class as standard conditions? These we have to know off by heart. We have to know our standard conditions off by heart. It might be a cheeky 1-mark question in an exam, but what are our standard conditions and what are the units for enthalpy change as well, for the most part? What are our standard units for enthalpy change, I should say? Anybody know? Standard conditions and our standard units. Kilojoules per mole, lovely, are our units. So lowercase k, capital J per mole, or you can write it as lowercase k, capital J, mole to the -1, still per mole. Either is fine. I'm going to sneeze. Am I? Yes, I am. Bless me. Bless me. Excuse me. Good. So kilojoules per mole is our standard way of talking about enthalpy change because it is per mole. So it's the amount of energy being exchanged per mole. And because we're talking about large amounts of energy, it's much easier to talk about it in terms of kilojoules rather than just joules, because otherwise we'd have massive numbers. So kilojoules per mole. Very good. Standard conditions is room temperature, which we pretend is a nice round 25 degrees C. Often it's not, often it's actually a bit cooler than that, or in the summer, a bit hotter than that. But we say that room temperature is 25 degrees C. However, we rarely give it in degrees C. We usually give it in Kelvin. So 298 Kelvin, capital K, which is 25 degrees C. To go from degrees C to Kelvin, you must add 273. So, and then brilliant, our pressure is 100 kilopascals, little k, kilopascals, or 1 atmosphere, but we usually give it as kilopascals, 100 kilopascals or 100,000 pascals, 100 kilopascals. Very nice. So usually our stated temperature is room temperature, which is 298 Kelvin. Okay, so when delta H is less than 0, is that exothermic or endothermic? When delta H is less than 0, i.e. negative, is this exothermic or endothermic? And therefore, do we know what the other one is? Which one's which? When delta H is less than 0 or negative, is it exothermic or endothermic? Is that an exothermic process or an endothermic process? So if you're not sure, you have to think about it in terms of the system. Okay, like I said before, the system is the thing we're interested in. So the system, if the system is losing energy, so energy is exiting the system, then the system is going to decrease in energy. So its enthalpy change will be negative. So that is an exothermic process. If the system is losing energy, because energy is exiting the system, so the system is losing energy, then the enthalpy change will be negative because the system has lost energy. So that will be exothermic, and therefore, if the enthalpy change is positive or greater than 0, then it must be the opposite, endothermic, because again, the system has gained energy. Energy has entered the system, so the system, the energy, the enthalpy per mole, energy per mole has gone up. So that must be endothermic. Okay, lovely. Let's keep going. So we need to be able to draw enthalpy change diagrams. Now, there is some discrepancy between exam boards about what is classed as an enthalpy change diagram and what is classed as an energy level diagram. So just bear that in mind, that sometimes they can show different diagrams. For the most part, if they've asked for an enthalpy change diagram and they want to see the progress of reaction, then you need to include a little bump, okay? So Usually the progress of reaction is a little hump that goes up from the reactants, up and then back down again to the products. And our enthalpy change, which is highlighted here, in this case will be negative because we've started at reactants, we've ended at products. So the enthalpy has gone down. So there is negative. Well done. I was just about to ask, therefore, oh, that's not an E, is it? Therefore, that is an exothermic change. Very good. It's an exothermic enthalpy change, and therefore the other one must be endothermic. And again, we must have the progress of reaction if we're doing an enthalpy change diagram. So we need to show the hump that needs to be gotten over. Now, bear in mind, the place where most people go wrong now is labeling the activation energy. So just have a quick think, where is your arrow going from and to for the activation energy? Because this is the most common error. Activation energy always starts at reactants and then it goes to the top of the hump. So the activation energy for an exothermic process starts at reactants and goes to the top of the hump. So is usually smaller than the activation energy, which starts at the reactants and then goes to the top of the hump for an endothermic reaction. Oh, I've not finished the word endothermic. I'll do that in a second. Okay, so it's not from the top line to the top of the hump. It's always from the reactants to the top of the hump. Okay, so here the activation energy is going from the reactants to the top of the hump. Let me just finish writing endothermic there. Which is often why lots of endothermic reactions need a bit of a kick to get going, because their activation energy is considerably higher. Okay. Does anybody have any questions about anything up to that point? Not, we're going to carry on. Lovely. So we also need to know how to calculate, or the definition, sorry, of standard molar enthalpy of reaction. Now, definitions are super important in chemistry. They always have been. So if we're talking about the standard molar enthalpy of a reaction, we can basically break down that name and work out what it is we're supposed to be talking about. So it's the enthalpy change. So I'm talking delta H of a reaction R. So the enthalpy change of reaction, and because it's standard, we have that little standard conditions 0 with a line through it. Looks a bit like a an underground symbol. So that means under standard conditions, which we've already decided are room temperature and pressure, so 298 Kelvin and 100 kilopascals. So that's happening under standard conditions. The little r is for reaction. Let's just put that in. Reaction. So it's the enthalpy change. Enthalpy change when a reaction occurs in the, now there's a couple of ways you can phrase this. I like to use the word stoichiometric ratios, but you can also say reacting ratios, or you can say correct balanced equation, using the correct balanced equation, something like that. So in the reacting or stoichiometric, reacting ratios, reacting ratios. And the reacting ratios given in the balanced chemical equation. And because it's standard enthalpy change, you always have to add in that caveat of under standard conditions. You don't have to give the standard conditions unless they've asked for them, but you do need to say under standard conditions. So how do we calculate enthalpy change of reaction? It's a really difficult thing to do in most circumstances because there's so much else going on in a reaction. So what processes or what things can we do in order to calculate standard enthalpies of reaction? Does anybody know what do we do in chemistry to calculate this? We often have to take a bit of a side route, and this is where Hess cycles comes in very handy. If we use, let's get my pen back again. We use Hess cycles or enthalpy cycles, they're also called. Hess cycles or enthalpy cycles. And there are two different types of data we can use, which can come in really handy. Either standard formation values or standard combustion values. Standard enthalpy of formation or standard enthalpy of combustion. That can help us hugely to work out the standard molar enthalpy change of a reaction. This is very difficult to work it out exactly what the energy change is from a set of reactants to a set of products. But if we can go via combustion data or via formation data, it can make it a lot easier. Or there are some that we can do using calorimetry. So we can use experimental data from calorimetry reactions, which we're not going to go into now, but that's our Q equals MC delta T lot of questions, that lot of theory, Q equals MC delta T. And then delta H equals Q over N. That section, which we're not going to go over today. Okay. So how confident are we feeling? So it's a really good idea if you're trying to become an independent learner, which hopefully you are as you're going through your A-levels, trying to learn independent working skills. Really good idea to have a quick check every now and again about how confident you're feeling. Do you think this is something that you need to go back over again? Or is it something that you're feeling pretty confident with and therefore you can kind of leave it for a bit and then just do some questions on later on? Or is it, oh my gosh, no, this is horrible. I'm going to need to go over this again very shortly because I'm missing it completely. So just take a second. If you want to, you can pop it in the chat just to let me know as well. It's quite useful for me to know how everyone's feeling. But a 1 or a smiley face if you're thinking this is fairly straightforward. A 2 or a middly face if, yeah, it's okay, I suppose. Or 3 and a face if you're super confused and it's horrible. So feel free to pop that in the chat. Let me know how you're doing. And then we'll have a go at an exam question in a second. So I'm just going to give you a second to have a look, think, and then let me know. And if anybody has any questions, obviously don't forget you can just pop them in the chat and I can hopefully have a go at answering them. Okay, should we have a look at this as try that again. Should we have a look at this as a past paper question? So this paper has given us a reaction. It's given us an enthalpy change. And personally, I would always go in and just have a look immediately about whether or not it is exothermic or endothermic. So what do we think? It's delta H is -9 kilojoules per mole. Is that an exothermic or an endothermic reaction? It then says the activation energy for the forwards reaction is 173 kilojoules per mole. It hasn't given us a positive sign, but it is a positive value because activation energy should always be a positive value. It's always energy going into a system, so it should always be a positive value. It then says, complete the enthalpy profile diagram below for the forwards reaction in equilibrium 3.1. On your diagram, label the activation energy, label the enthalpy change of reaction, and include the formulae of the reactants and the products. So they want to make sure we know exactly what we're talking about. So, is this endothermic or exothermic? What do we think? Is this an endothermic or an exothermic change? Any ideas? Because it's got a negative enthalpy change, given up the top here, we know it must be exothermic, which means the negative enthalpy change is telling us that the system has to have lost energy. So the enthalpy of the reactants must be lower than the enthalpy of the products. That's why they've put their reactants line in the middle, because they want you to have the option to go above or below. They want to know if it should be above or below, and it should definitely be below, because this is an exothermic reaction. So the enthalpy change, well done Sophie, the enthalpy change is negative. So that change is our enthalpy change, which is minus 9 kilojoules per mole. It's not massive. It's not a massive enthalpy change. It's only tiny, but it is still an enthalpy change. So they've asked us to label the activation energy. So I need to show the progress of the reaction. I've just gone straight through my writing there, but never mind. I must show the progress of the reaction. And then I need to label my activation energy, which is from the reactants to the top of the hump, always. So that's the first one. I need to label the enthalpy change of reaction delta H, which I have done as well, tick, tick. And then include the formulae of the reactants and the products. They've asked us for the forwards reaction. They've specified that. Excuse me. So just got to be careful that they haven't specified the backwards reaction for some weird reason. Most of the time, it would be the forwards reaction. And as an aside, which I didn't mention earlier, because they've written the enthalpy change of reaction on the right-hand side, and because 99% of the time, the enthalpy change given is for the forwards reaction, that enthalpy change is for the forwards reaction. So if for some reason they'd given us the enthalpy change for the forwards reaction, but then they'd asked us to show the enthalpy profile diagram for the backwards reaction, then it might make it a little bit harder. They haven't. It's all for the forwards reaction, so it's not as complicated, but I do need to make sure that I write down all of the formulae of the reactants and the products. So my products are 2HI. It's all given to me, so I don't have to work anything out, which is nice. I just have to make sure I've written them in. And have I done everything? I've done everything. Lovely. So that would be worth probably 2 marks. Okay, if anybody has any questions, just pop them in the chat. Otherwise, we'll keep going. So we're going to have to think about enthalpy change of reactions and how we can calculate them. So we've had a think already about what we can do. Let's put that into practice. So Hess's law, we've touched on this already. Hess's law, or the enthalpy law, allows us to use enthalpy cycles for calculations, and is as a result, I think that's supposed to say, and is as a result of the law of conservation of mass, of energy, etc. The law of conservation of energy specifically is that energy cannot be created or destroyed, only transferred. Energy cannot be created or destroyed, only transferred. And because of that, Hess's law comes into being. What is Hess's law? Does anybody know what Hess's law is? It's a very useful law, and it you know, it's a hard one to get your head around, but it does make sense when we've got our head around it. It can make sense, which is useful. Anybody know what Hess's law is? It is one of the things that is in all of the specifications as needing memorizing. So we do need to know off by heart what Hess's law is, including keywords and phrases. So it's important that we learn it ASAP, basically. The Hess's law states the enthalpy change for, oh my goodness, what was that word? Let's try that again. Enthalpy change for a reaction or process is independent of the route taken. What we mean by that, and if we think about it in another way, is we're thinking about the difference in energy between A and B. All we're interested in is the difference in energy between A and B. So if you're a mathematician and you've got a good concept of vectors, you understand vectors, it's a similar thing. If you know about displacement, the displacement between your house, A, and the school, B, the displacement between the two will be identical, whether or not you've walked straight there, or you've taken the bus around the houses. The displacement between A and B, the direct difference between A and B is the same. Doesn't matter how you got there, because the displacement between the two will always stay the same. And it's the same thing here. The energy change, or the energy difference between reactants and products, between 3 lots of A and 2 lots of B, let's say, and 2 lots of C and 2 lots of D, doesn't matter if we started with our A and B and we've gone all around the houses to get to C and D, or if we've gone straight there, the difference between the A and B and C and D is the same. It's the same concept here. The enthalpy change for a reaction or process is independent of the route taken. And because of that, we can use Hess cycles to calculate these enthalpy change of reactions. So let's have a look. Script on, there we go. Okay, so this is another thing that we need to memorize. It's standard enthalpy of formation, the standard enthalpy change of formation. Does anybody know what it is? It's delta HF, F for formation, delta HF. What's the definition of enthalpy change of formation? Another definition that we need to know off by heart. Does anybody know? Make that look a little bit nicer. So all of these definitions need to be learnt off by heart. Oh, very nice, Sophie. That looks almost perfect. The only thing is, what do we need to add on the end if it's standard enthalpy of formation? Otherwise, that's perfect. So it is the enthalpy change, or the heat energy change, when, absolutely right, 1 mole. So it's all enthalpy is per mole, which means for the most part, apart from enthalpy change of reaction, which is a bit awkward, a bit more awkward, it's going to be 1 mole in there somewhere. Okay, we're either forming 1 mole, or we're breaking apart 1 mole, or we're using 1 mole. Because it's per mole, we need to have a number of moles in there somewhere. So for standard enthalpy of formation, it's forming 1 mole of a compound. Okay, so we need to have that amount in there, that 1 mole. So the enthalpy change, or heat energy change, when 1 mole of a compound. Now it needs to be, oops, can't spell. It needs to be a compound because it needs to be made of more than one thing, more than one element. 1 mole of a compound is formed. You can say substance, but compound's more specific and a bit more accurate. But a substance would still get you the mark. 1 mole of a compound is formed from its constituent elements. And you don't have to say constituent because it's assumed, but I like to say it. Constituent elements in their standard states is just the extra bit we need to put on the end. Standard states under standard conditions. And what I mean by that, oops, can't spell. What I mean by that is standard conditions would be, for example, oxygen is in this, standard states, oxygen is in the state gaseous under standard conditions. In room temperature and pressure, oxygen is in the gas state, water is in the liquid state, nitrogen is in the gas state, chlorine is in the gas state, sodium is in the solid state, etc. So it's elements in their standard states, whatever their standard state would be under standard conditions, under room temperature and pressure. So it's the enthalpy change when 1 mole of a compound, we're making 1 mole of a compound from its constituent elements in their standard states. So here we go, we've got a reaction of what looks like glucose, combustion of glucose. This is our reaction, this is the thing we're trying to find out, because we don't know what the enthalpy change of turning glucose and oxygen into carbon dioxide and water. So if this is, or maybe we would want to put this oxidation. Anyway, it doesn't matter. This reaction is what we're trying to find the enthalpy change for. So, but we don't know how to get there directly. But what we do know is how to get there indirectly. And we can go via enthalpy of formation data. So let's have a think about how we form glucose, how we form C6H12O6. We need some carbon. We actually need 6 moles of carbon, as in carbon solid. That's carbon in its standard state. We need hydrogen gas. That's hydrogen in its standard state. We need hydrogen atoms. And we're going to need 6 moles of hydrogen. And we need 3 moles of oxygen. But then we're also going to need 6 moles for the combustion, actually. So we're going to need 9 in total to make glucose. Notice the direction of the arrow. The direction of the arrow is I'm going towards the thing that I'm making. If I'm forming glucose, glucose is the thing that I'm forming 1 mole of, I'm forming glucose, then the arrow must point at glucose, okay, from the constituent elements to the thing that I'm forming. So because this is enthalpy of formation, immediately my brain's thinking formation, what's the definition? It's the enthalpy change when 1 mole of compound is formed from its constituent elements. So what are its constituent elements? I've written those down. Check which way the arrow is pointing. It's pointing at the thing that's being formed because that's the process. And that's my enthalpy change of formation there. Enthalpy change of formation of glucose, C6H12O6. On the other side, what am I forming? The compounds I'm forming are carbon dioxide and water. But again, look back at that definition. The definition is the formation of 1 mole. I'm actually forming 6 moles of carbon dioxide. So I've got 6 lots of the formation of carbon dioxide. And although I haven't given myself enough space, I'm forming 6 lots of water, 6 moles of water, 6 lots of the enthalpy change of formation of water. And again, the arrow needs to go towards the thing that is being formed because that's what the process is describing. So then how do we work this out? How do we use a Hess cycle with this? Well, I always say, because it's appropriate when you go to do year 13 Born-Haber cycles, which is kind of a step up-ish, we're trying to work out the enthalpy change from the beginning of the arrow to the end of the arrow. That's the process that we want to see from the beginning of the arrow to the end of the arrow. But we can't go directly there. So if we can't go directly there, but we still want to start at the start of the arrow and end at the end of the arrow, the process we want to see is going from there to there. We want to go around the other way. We must start at the same reactants, finish at the same product, we're just going around a different route, which means we've got to go against that process. So we're going against that arrow, but with those processes. So overall, the equation that I'm using to work out the enthalpy change of reaction here is I'm going against the formation of glucose, so minus the formation of my reactants, in this case glucose, but I'm going with, so I can add whatever that value is, plus 6 lots of the enthalpy change of formation of my products, which in this case is carbon dioxide and 6 lots of enthalpy change of formation of water. So it's minus enthalpy change of reactants plus enthalpy change of products. How are we doing for time? Better whiz on. Okay, so this is formation. We're using formation data. Now it is the same every time, but the questions that are given to you are a little bit tricky. So don't rely on rote learning here. Really understand why the arrows are pointing in whichever direction they're pointing in and why you're minusing and plussing, because it will make life a lot easier when you come to do your calculations. You know, why have we got 6 lots of one and only 1 lots of the other, etc. If you want to go back, when this appears as a recording, go back into this and back through that and just check that you're happy, because I've done quite a lot of explaining there to try and help you to understand why our arrows are pointing in all the same directions, why we've got 6 lots, 1 lots, etc. Okay, what about with combustion though? We're going to need to speed through this a little bit quicker because we're running out of time. If we're, again, we need to think about enthalpy change of combustion, we need to think about the definition. So, that's not a triangle at all. Try that again. That's it. Triangle, combustion, C for combustion. That's the enthalpy change of combustion, standard enthalpy change of combustion. So we've got a little standard symbol. What's the definition? We are slightly running out of time, so I'm going to speed through it. Do we know the definition of a standard enthalpy change of combustion? It's similar to formation, but not the same. So it's the enthalpy change, or you can say heat energy change when, and same as formation, it's 1 mole of a substance burns completely in oxygen. And burning completely in oxygen is complete combustion. So you could say, very nice, Sophie, well done. You could say, because it says when 1 mole of a substance burns completely in oxygen, you can say undergoes complete combustion. But I like to include the term oxygen because it reminds me that there's oxygen involved, and that's sometimes forgotten. So enthalpy change, heat energy change, when 1 mole of a substance burns or reacts fully or completely in excess or just oxygen. As long as you talk about it being full or complete, you know that there is enough oxygen, completely in oxygen. Very nice, very good. So in this case, again, when you're constructing Hess cycles, I like to write whatever I'm trying to find across the top because it makes my life a lot easier, and then fill in the rest of it. You don't have to, but I think it's a nice kind of process to go through. This is what I'm trying to find. This is the enthalpy change of reaction I'm trying to find across the top. The data that I will have been given must be enthalpy of combustion. So I'm going to look at the data table I've been given. if it says delta CH, change of combustion, then I'm thinking, right, I'm drawing a combustion cycle, which means the bottom of my cycle will be combustion products. What happens when we burn C2H4O? It's an organic substance. It's not a hydrocarbon, but it's still an organic substance, which means there's only going to be two products. The two products are going to be carbon dioxide and water. Likely gaseous water, but we don't know for certain. How many moles of each are we going to form? Well, there's going to need to be 2 moles of CO2 formed because there's 2 carbons in the starting product. And there'll be, there's H2 there as well, which is also burning. So that's going to need to burn. That's going to need to burn. 1, 2, 3, 3 moles of water are going to be produced, which means in total, I'm going to need to use 3 moles of O2. I'm also looking at the direction of the arrow. So, Quadro, this might help you a little bit with your aligning of the processes. This is where definitions are key. Yeah, if you're confident with your definitions, if you know what you're trying to represent with these arrows, it makes constructing the Hess cycle so much easier. So my arrows have to point down in this case because I am burning the substance. I'm burning the compound or the element, whatever it is. So if hydrogen is being burned in oxygen to produce water, the arrow's got to start at the hydrogen as my reactant and end towards the water as my product. You can put a box around everything if you want to make it a bit easier. You don't have to point your arrow directly at the right product. But equally, my ethanol on the right-hand side, I need to point the arrow down because if I'm burning ethanol, if I'm combusting ethanol to produce carbon dioxide and water, the arrow is pointing in the direction of the process. I'm burning it, so I'm producing my carbon dioxide and water at the bottom. Therefore, my arrow must go in that direction. So again, in order to work out how to construct my Hess cycle, I want to start at the beginning of the arrow and end at the end of the arrow because that's the process that I'm trying to calculate. But I can't go directly there, so I've got to go around the houses. So that means I've got to go around and up. Bit of a wonky one there. Let me just do that again. Doesn't matter. I'm just going to make it a little bit easier to read. There we go. Okay. So that means I'm going with these 2 arrows now. I'm using that process, but I'm going against the other one. The 2 arrows on the left, they are enthalpy of combustion of H2O and enthalpy of combustion of C2H4O. And the arrow on the right that's pointing down, the one in blue, I should have done that in blue, otherwise it's going to get confusing. Sorry. Let's just write that in blue. So sorry, the one on the right-hand side is enthalpy combustion of H2, and the one on the, did I say left? The left-hand side is enthalpy of combustion of H2, and the one on the right-hand side is enthalpy of combustion of C2H4O. And then the arrow on the other side of the Hess cycle is enthalpy of combustion of ethanol C2H5OH. So when I'm constructing my equation, if I'm trying to work out my enthalpy change of reaction, I'm going with the combustion data for H2 and C2H4O. So I'm adding the enthalpy of combustion data for those 2, whatever those values are. But I'm going against the other arrow. So I need to minus whatever that value, whatever that arrow is representing. C2H5OH to construct it. So how are we doing for time? We need to speed on a little bit. So should we put that into context? Let's construct a Hess cycle and have a go at creating, putting some numbers into this process. Just have a quick think as well. I won't wait around for too long here, but have a quick think about how confident you're feeling. And then we're going to have a go at putting some numbers into it to see if it can solidify it in your brains. We'll come back to this one if we have time. I'd like to have a go at this one first because it's talking about constructing a Hess cycle. This is the second exam question. Okay, So it says methane burns in a limited supply of oxygen to give carbon monoxide and water. That's our reaction that's happening. The enthalpy change for this reaction cannot be determined directly, but can be found using the standard enthalpy changes of combustion of methane and carbon monoxide together with Hess's law. They've told us in the beginning of this question that we're using enthalpy of combustion data, so that's a bit of a hint. Standard enthalpy changes of combustion needed are for methane as that value and carbon dioxide as that value. That's the enthalpy changes of combustion for methane and the enthalpy change of combustion for carbon monoxide. Draw a Hess's law diagram which would enable you to calculate the enthalpy change for the combustion of methane to carbon monoxide, that process, that reaction. And they've given us that to begin with. So first things first, whenever we come across an enthalpy change, Hess's law diagram, I'm always looking at what data am I using. I'm going to be using enthalpy change of combustion data, which means the arrows I include or the numbers I'm going to be representing are for enthalpy of combustion. So what is that? Enthalpy of combustion is the energy change when 1 mole of a compound burns completely in oxygen. So when methane burns completely in oxygen, I'm going to form carbon dioxide and water. I can add my oxygen in if I want to. But one thing I haven't mentioned is the enthalpy change required to turn O2 into O2 is 0, to turn something into itself, or we're not doing anything. So the energy change is 0. So a lot of the time you might see, for example, oxygen as a reactant here, but if I burn oxygen in oxygen and produce oxygen, then nothing's happening. I'm not changing anything. So the enthalpy change associated with that is 0 because it's not an enthalpy change. So you don't have to include those enthalpy changes if they're 0, but you can choose to, and sometimes they do like you to include them as well. I'm not going to in this case, I think it adds to the confusion. So I'm just going to put that in brackets as a reminder. So when I burn methane in oxygen, and when I combust methane, I'm forming carbon dioxide and water. I'm going to be forming 2 moles of water and 1 mole of carbon dioxide. Actually, I've got the O2 there. What am I about? I don't need to put it there. It's right next to it. Oops. Sorry, it's there. So I don't even need to include it. Okay, and then if I'm burning carbon monoxide, I'm going to form 1 mole of carbon dioxide, and that's it. Again, enthalpy change for turning water into water is 0. So I could include an arrow there if I wanted to, but it's 0. The change from turning water into water is 0. So I don't need to include that. And I'm not going to, because I think it adds to the confusion. So we're trying to work out that reaction process. But if you want to, if you can, see if you can jump ahead of me now and come up with an answer for this question. Come up with a calculation for part 2. If you need to, though, hang back with me and we'll get there a bit slower, just in time to finish the lesson. So we want to go directly there, but we can't. So we've got to go around the houses, which is involving going that way and that way. Because we've got to go around from the beginning of the arrow to the end of the arrow, which means we're going with the first arrow, but against the second arrow. So what do those arrows represent? What numbers do they represent? Combustion of methane, we've been told, is minus 890 kilojoules per mole. And the combustion of carbon monoxide is minus 283 kilojoules per mole. Because I'm showing what that arrow is representing, I am writing those values in as they are given, because that is what that arrow is representing, the blue arrows. When I'm constructing my equation, I want to know what the enthalpy change of reaction is. So I'm going with the first arrow. The first arrow is minus 890. So I'm adding minus 890. and then I'm going against the second arrow, so I'm minusing whatever the second arrow is, and the second arrow is minus 2H3. Then I can resolve my symbols, normal basic mathematical laws. Plussing a minus is a minus, minusing a minus is a plus, which means if I simplify that equation before I plug it into my calculator, I've got minus 890 plus 283, which means the overall enthalpy change is minus 607, apparently, according to the numbers I've got in front of me. Kilojoules per mole. And that is my final answer. Okay, we have just run out of time, so I'm going to pause it there. But I will just go back. Oh no, I'm pressing all the wrong buttons. Stop. I will just go back a slide and just say, if you want to have a go at this one at home, the correct answer is D, plus 63 kilojoules per mole. So have a go, see if you can work that one out yourselves in your own time. Don't forget that the direction of your arrows is incredibly important. And as we've done here, I would highly recommend, especially if you're new to these or you're not quite as confident, construct your equations as I've done here, okay? Put the number in brackets that the arrow is being represented by, and then a plus if you're going with the direction of the arrow, or a minus if you're going against it. Then resolve your pluses and minuses, and then plug your numbers into a calculator. Okay, so we have looked at the concept of enthalpy and change in enthalpy. We've looked at Hess's law, and we've looked at making some simple calculations with enthalpy cycles. Does anybody have any questions? If not, hopefully this has been useful to you. Please feel free to go and have a look at our other web classes. We've got ones on maths, biology and physics as well. Keep an eye on our schedule, because there should be some coming up over the summer. And then we will be definitely restarting our sessions in September as well. If you're interested, go and check out the snapdevice.co.uk website, because there's details of our weekly web classes that we have on there as well. So if you want more web classes and access to all of our Snap Device content, then head on over onto the website and have a look at that. And don't forget to have a look back through the YouTube channel and watch any videos that you think might be useful. Good luck with your revision over the summer. If you're a Year 12 student, it's a good time to get on top of Year 12 content, so that when you're introduced to new stuff in Year 13, you are not as behind as you might otherwise be. And if you need help with that, obviously, feel free to get in touch with SnapRevise and see if you can have a look at what we've got on the website. Yeah, so such as the subscription resources, exactly. Lovely. Have a great summer. Hopefully see you guys maybe at a future web class, a future Sunday session. Thank you very much, guys. And we will see you soon. Bye.